In this video, I'm going to talk about how to calculate changes in linear momentum. So in this situation, I have a ball of mass, 3 kilograms, traveling at a 45-degree angle at 6 meters per second. It's going to hit a wall or other object, and it's going to bounce off at 5 meters per second at a 35-degree angle. Normally, these two angles should be equal, angle of incidence and like angle of incidence reflection, but because of some English or spin on the ball or something like that, the angle changes. At any rate, we want to find the change in linear momentum. So the change in linear momentum is relatively simple. It's delta p, and changes are always final minus initial. The one twist in this problem is that the initial and final momenta are an angle, so they're x and y components. And since momentum is a vector component, we need to make sure we calculate these things correctly. So when we do these type of problems, I'm going to write the momentum vectors in I and j components. So I'm going to take that first velocity vector or first momentum vector. So if I take 3 times 6, that's going to give me 18 for the momentum initial kilograms meters per second. And I basically want to break it up into sine and cosine components. And this is a 45-degree angle here. So using sine and cosine with a 45-degree angle, I'm going to write the initial momentum is equal to, and I've done the calculations, which is 18 cosine 45 in the I direction, 45, minus, because it's downward, minus 18 sine 45, which gives us a grand total of 12.73 I minus 12.73 J quantity kilograms meters per second. Okay. Likewise, I'm going to take the final velocity vector and break it up into its components, which should look something like this. And using the same trigonometric functions, I get a value of, and you can verify these values, of negative 12.28 I, because it points to the left or negative direction, minus 8.6 J kilograms meters per second. So basically what I've done is I've written the initial and final momentum vectors in terms of their I and j components. So going back to my original delta equation, I basically need to do a vector subtraction. In other words, I need to take corresponding i's and j's and subtract. So this becomes negative 12.28, this is the final, I minus 8.6 J, that's the final, minus the initial. And what's the initial? The initial is 12.73, oops, 73I minus 12.73J. And so what I do now is I take corresponding components. So I take a negative 12.28 minus a negative 12.73, and that becomes 25.01 I negative. Then I take negative 8.6 minus a minus 12.73, so that gives me negative 4.13 J kilograms meters per second. So in a nutshell, and that's your final answer, that's delta P. So in a nutshell, if I can write the momentum vectors in terms of their I and j components, then I can take those corresponding I and j components and subtract. One last note. So what does this mean? If I were to draw this vector, it would actually be a vector that's 25 along here and minus 4 this way. This would be 25 minus and negative 4 approximately. It's a vector. The delta p vector represents is this guy right there. And if I take a look at what happened, it looks like there's a large x component. So what happened was, and that makes sense because when the ball hit the wall, it had not only had to take its x momentum to 0, but had to reverse it. There's a large change. Slow it down in the x direction to 0, and then rebound it back in the x direction. In the y direction, it's not as large, negative 4, because I'm already moving down, and I'm still moving down because I have a lower velocity because of the collision, and the angle because of some English with the collision. It's going a little bit slower, different angle. The change is not as big as minus 4. So the resulting vector that you just calculated, negative 25i minus 4j, represents what happened to the ball during the collision. So if I can write the momentum vector in I and j components, whatever they may be, I can just simply take final minus initial, taking corresponding i's and corresponding j's, subtracting, and getting a final answer.